Hello everyone, I am by Yunpeng. I am glad to present our paper, Heads-Up Multitasker, Simulating Attention Switching on Optical Head-Mounted Displays. On behalf of all our collaborators, heads-up computing has been a novel interaction paradigm that facilitates efficient digital interactions, such as information acquisition during daily activities. Under such a picture, optical head-mounted displays, or OHMDs, emerge as a useful platform to display digital information while users are multitasking with physical activities. However, new challenges appear as humans need to balance their limited visual attention across different tasks. The nature of multitasking using OHMDs poses significant challenges in designing systems that effectively balance and optimize the limited resources of visual attention. Additionally, these designs must also consider safety issues. To overcome these challenges, a comprehensive and systematic understanding of user attention allocation within OHMD is essential. In this work, we developed a computationally rational model that simulates users' multitasking behaviors when using OHMDs while walking, including attention switch, walking control, and reading control. In detail, the model predicts how to look, when and where the simulated user agent should focus on, digital word on OHMDs or environmental signs, and how to walk, how fast to walk and where to walk. Existing computationally rational models on multitasking are mainly focused on other safety-critical areas, such as driving, but could not address the distinct challenges posed by using OHMDs, where massive attention switches happen, and agents need to decide how to sample information from both OHMDs and the environment. As for traditional models that cater to multitasking, such as ACTR and EPIC, they fall short in adaptability and rational analysis. Since modelers need to handcraft users' interaction strategies, policies, and state action pairs in the visual scene. In our model, instead of manually construct every simulation step, we use a physics engine, MuJoCo, to render an agent that has actual mobility and visual perception in the simulation, and frame user behavior as boundedly optimal policy. We solve such policies using reinforcement learning, where the agent used trial and error experience data obtained through interactions with the simulation environment itself to find optimum. Thus free modelers from handcrafting everything. However, no free lunch. Technical challenges emerge as how to frame user behaviors as solvable optimal questions. Our model features a hierarchical structure that decomposes the complex multitasking into simpler subtasks that happen at different timescales and perceptual levels. As shown in the figure, from left to right, 3 levels bridge the internal state, where agents' mental activities happen, and the external state, where human-computer interactions happen. The motivation of using hierarchical reinforcement learning (HRL) is twofold: break down long-horizon tasks into solvable and trainable subtasks, enable high-fidelity simulation of the primitive actions, such as nuanced oculomotor control with realistic visual perception. As for 3 levels, the supervisory controller (SC) first determines the high-level attention deployment. Look at the digital content on OHMDs or environment. Once the attention is allocated, the task-level middle module will determine the actual visual targets, which word to read on OHMDs or which stimuli to attend to in the environment. After the target has been determined, the agent calls the oculomotor control (OC) and locomotion control (LC) to manipulate the visual attention and mobility in the MuJoCo simulator, thus performing the task. Computationally rational models feature in using partially observable Markov decision processes to describe human behaviors. The workflow and rationality behind could be summarized as such. Frame ideal human users as rational entities. They try to maximize rewards while minimizing penalties. We frame user behaviors as sequential decision-making processes, which emerges as consequences of boundedly optimal policies. POMDPs have been proved to be suitable formalisms to describe such processes. Human users are constrained in limited cognitive resources, thus needing to sample information from the environment, such as moving eyeballs to obtain the environmental information. Thus they are always only partially aware of the world. This partial observability is coherent with the POMDP formalism. To find optimal policies that represent users' interaction strategies, we use reinforcement learning (RL) to solve framed optimal questions. In detail, we have trained different models to conduct tasks at different levels. At the supervisory level, the agent needs to decide when to read words on OHMDs and when to check environmental stimuli. There is a trade-off. If being too engaged in OHMDs, the agent will miss environmental information. If being too cautious about the environment, the agent could not read properly from OHMD. Meanwhile, the agent needs to determine how fast to walk. If the agent walks too slow, it is hard to finish tasks. If the agent walks too fast, there are too many head perturbations that affect reading. In the task level, as for the read model, it tackled the problem of how to relocate as soon as possible. Attention switches cause reading interruptions. When the agent decides to read again, it needs to resume the reading task by finding the correct left word. The agent's task is to balance speed and accuracy. Find the correct word to resume reading as soon as possible. At the motor level, oculomotor locomotion control take care of executing primary actions, such as eyeball rotation and walking speed control. In the example of the oculomotor control, with the given word index and image rendered in the simulator, the agent needs to learn how to rotate its eyeball to fixate on the targeted word displayed on OHMDs as soon as possible. Moreover, it has to learn this process with shakings and visual deterioration due to head perturbations during walking. To evaluate the efficacy of our model, we conducted 4 studies. Except the first study, the rest are coupled with human data comparison for evaluations. The gist in our evaluations is, the agent and the human participants do the same task. If the simulated results, model predictions, have a high alignment with human data, then the model is reasonably good. Study 1, 2, 3 are separately evaluating 3 key components. SC, OC, and R. Study 4 is an overall study evaluating the whole model together. In Study 1, we simulate that the agent's attention switch behaviors as an adaptation to their task priorities. The left agent Shakespeare prioritizes reading more than walking compared to the right agent Olaf. So Olaf is more focused on walking and has more attention switches to the environmental signs. Similarly, agents' attention switch behaviors also adapt to their walking speed. Faster the speed, more need to switch attention to keep environmental awareness. The left slow agent switches fewer times compared to the right faster agent. In the simulation, the number of attention switches emerges as an adaptation to agent's task priorities and walking speed. This adaptation also applies to the reading interruption position, reading speed, and walking error rate. In Study 2, we evaluate the model's ability to simulate the effect of head perturbations on the reading performance. When walking, such shakes on the digital display can decrease one's reading speed. By comparing human data and simulated results, the model can accurately replicate the phenomena of reading speed decrement with low discrepancy. In Study 3, we evaluate the model's capability of replicating humans' reading resumption behaviors after the attention switch. The reader needs to scan words to find the one at last read and resume reading from there. The empirical work has found text spacing layout affects users' reading resumption performance. Following their setup, we replicated it in MuJoCo and evaluated 3 layouts, L0, L50, and L100. We evaluate the simulated reading resumption time cost and error rate against human data. The simulated results in light green have a high alignment to human data in blue. Figures show the model can accurately replicate human behaviors as an adaptation to the 3 layouts. The darker green parts refers to ablation studies of removing the key component, Position Memory Module, PMM, and Reentry Position Module, RPM in the model. There appears a dramatic discrepancy when without this PMM or RPM, which further reflects their importance in the model. Furthermore, we ablated the parameter inference, pi. Results show model performance only decreased a little. These show that our model is capable of generating simulations that conform to human behavior, even when not explicitly calibrated with human data, offering the potential for predictions in scenarios lacking human data. In Study 4, we assess the comprehensive abilities of the model within a single integrated task, building upon prior empirical research. Participants' agents were instructed to navigate a rectangular path while simultaneously paying attention to signs on the walls and reading text displayed on OHMDs to the best of their ability. The challenge lies in maintaining an optimal walking pace. Walking too quickly could negatively impact the reading experience, as shown in Study 2, while failing to adequately notice and respond to the signs could result in task failure. This task is characterized by its demand for intricate control over attention distribution, walking pace, and the resumption of reading. It also explores the interplay between these elements. Our model demonstrates successful replications of step-by-step walking and attention control. Apart from that, our model could replicate users' multitasking performances in terms of aggregated metrics, including attention allocation, walking speed, and reading resumptions. Our model, which successfully replicates human behavior in tested conditions, can also be used to predict outcomes in new unseen conditions like L25, L75, and L125. This makes it a useful tool for simulation, allowing us to predict how humans might perform in these scenarios before actually conducting human studies. It also enables us to test a wider range of conditions in more detail, providing designers with valuable insights without the need for a large number of preliminary human studies. To conclude, our modeling methods, POMDP formalisms, are sufficient to describe users' multitaskings with given context. HRL is a suitable approach to model complex multitasking and support high-fidelity simulation at different levels and timescales.